Hello and welcome back to this 35th lecture on biomicroelectromechanical systems. Let us do a quick preview of what we did in the previous lecture. We started designing of peristaltic micropumps and their flow rates through an integral technique wherein we would take an area, a radial area, and try to use the deflection of a thin membrane and then try to integrate the whole deflection, saying that what would be the amount of volume change delta V because of this deflection. The deflection would be caused by some kind of an energy mechanism, and thus this volume change multiplied by the frequency for low frequencies would actually give you the tentative flow rates for the particular micropump. We also talked about different forms of micropumps, especially the non-conventional types like ferrofluidic types of pumps, wherein there were two geometries. One was just a simple planar mechanism where with an external magnet. Another was a circular path of fluid flow with two parallelly placed magnets, where the magnets would flow with or move with respect to one another, with one fixed and another moving, and it would drive the fluid inside out the pump as a plug. We talked about valveless rectification pumping systems and osmotic membrane type of pumping mechanisms, so on and so forth. Then we kind of went into the fabrication processes and tried to look into basically silicon, because silicon was essentially the primary MEMS material that was brought from the that was translated from the silicon industry. You may recall that MEMS processes were essentially fallout of the microelectronic processes which were generated by the semiconductor industry, and due to the integration density problems those processes were made obsolete. So MEMS kind of took it up. So silicon definitely was the most prominent material which could start with building MEMS, okay, and also bio-MEMS. So we talked about crystalline silicon and their characterization modes and various notations which would be representatives of the directions in the planes or the group of planes. And then we talked about this famous Okralki's method of growth of single crystalline silicon, which is normally used in the industry for producing wafers. Today we will be looking into another aspect of single crystalline silicon formulation, and that is essentially also known as the float zone method. As you can see here in this particular example or illustration, the float zone method is really different than the Okralki's growth method, and essentially this is used for making crystals which are lower in diameter or size than what Okralki's can normally make. So the way you make it is essentially by taking a polycrystalline supply rod, as you can see here in this figure, and this rod is kind of pushed through this small orifice in this region, and while it is being pushed and immediately before it is being pushed, it is superheated in this particular zone by using either some kind of an RF coil which is around this region, or using infrared radiations to a great extent, or using laser. For example, so all these heating modes are non-contact in nature, okay, and so therefore there is a tendency of no thermal gradients to be caused within this mold, which would be an important advantage of this method over the Okralki's growth method, where the heating is done essentially through the sides of the crucible. Now as this is heated up, and this is essentially, this outer is essentially a quartz tube, okay, that is what the outer is. This whole outer is made up of quartz, and so you have this necked region through which the liquid flows, and on the other side here you have a seed crystal. So this essentially, this part here, as you are seeing, is the seed crystal, okay, and as you are actually dipping the crystal down all the way to here, and you have the silicon melt going in, you essentially take this away now with a certain velocity v1, while this other outer is rotating, okay. And so as you are feeding the liquid material through the necked region into this region, the seed grows the material around it and in the same direction as the seed crystal, and therefore you have this wafer which comes out in this end totally of the same type as the seed crystal were. The advantage in this method is that it is free of any thermal gradients which may happen due to the other form of heating in Okralki. The number two is that the material has a higher purity of silicon, because fused silica which is melted is essentially passing only through a quartz environment, as opposed to the Czochralkis, where you can have, and also there is no question of any the whole process is carried out in vacuum. There is no question of any gas entrapments here, because the melt essentially is formulated in the backside or as a plug, and this particular thing is the solid material which is a plug. So, there is no intrusion of gases really, and it is more pure, or it is a high purity crystal that you can obtain by using the float zone method. So, in a nutshell, this method is used for extremely high purity silicon growth. A rod of high purity crystalline polycrystalline material is held in a chuck, while a metal coil driven by high power radio frequency signal is also slowly passed along its length. Alternatively, a focused E-beam can also be used to heat the rod, or an RF frequency is used normally. The field set up by the RF power leads to eddy currents and joule heating, and the material is melted away. To enhance the growth along the preferred crystal orientation, a seed crystal is injected into the top of the molten rod, and in this technique a thin neck of 3 millimeter diameter and 10 to 20 centimeter long is pulled, and the pull rate and the temperatures lowered to shoulder the crystal out to a larger diameter, thereby making a large diameter crystal of at the other end. Okay. Argon gas of course is flown through the tube for maintaining the inertness and the non inclusion of oxygen or any other moiety into the crystal. So, this is another form of making silicon polycrystalline or single crystalline silicon from polycrystalline silica material, and essentially this kind of piggybacks the other Czochralkis process whenever purity is in question and high pure material is needed. Let us now look into some of the specifications that such wafer outputs would have from both the processes. So, essentially the silicon bowl that is finally emanated from both the processes, whether it is float zone or Czochralkis, is first characterized by its resistivity and crystal perfection. Okay. So, there may be point defects which may alter the resistivity significantly. There may be dopants which are introduced in the melt for getting p type or n type material generally. So, this is one first aspect, that what is the resistivity of the crystal and what is the level of perfection of the crystal. Are there many defects or are there lesser defects? So, then the seed and tail are cut off and the bowl is mechanically trimmed to proper diameter. So, essentially now this proper diameter is the diameter of the wafer that is in question. Diameter at this point really is slightly larger though than the final wafer diameter, because you have to have some allowance for polishing the sides. Additional etching probably has to be done, and then that is followed by chemical mechanical polishing. The wafers for wafers less than 150 millimeters flats are ground the entire length of the bowl to denote the crystal orientation and the doping type, and so therefore there is of course there is a flat side on one end of the bowl which can denote what kind of crystal orientation the silicon crystal would have, or what is the doping type, and basically the largest flat called the primary is oriented perpendicular to the 100 direction. Okay, that is what you have to remember. So, any silicon crystal is denoted by this flat, the largest flat on the side which is perpendicular to the direction of the 100 crystal, and this can be evaluated by lattice diffraction methods at the very beginning. This is a kind of industry standard that they put for you to figure out what the direction of a certain direction would be of a particular crystal, if you know what is the perpendicular direction to the 100 direction or 100 plane. Okay. So, you can see here this is really the top view of such a wafer, and you can see at this end particularly the flat is grounded, which means that this is probably the plane which is perpendicular to the direction 100. Okay. So, the direction 100 really is perpendicular to this, that is what essentially it means, and then also this can be used to denote other kind of about the resistivity. Like for example, this is a 111 p type, this is a 111 n type, this is a 100 p type, okay, this is a 100 n type, so on and so forth. So, there are different specifications which the silicon industry would give for denoting these wafers. Other important aspects here are the full specs, where it considers what is the cleanliness in particles per centimeter square, what is the oxygen concentration, the carbon, the metal contaminants in the bulk in parts per billion. You can also talk about growth in or grown in dislocations per centimeter square of the surface area of the wafer. You could talk about oxygen induced stacking faults. You could also this is in the volume, of course, stacking is an effect in the volume. You could talk about diameter in millimeters, you could talk about thickness in microns, the bow of the wafer, how much the bowing happens or the warping happens, the global flatness, which is in micrometer, and then of course the cost. So these specifications are normally specified on the characterization box associated with any new wafer which comes in. On the other hand, some of the other materials like glass normally consist of silicon oxide, which is about 68% in soda lime, 81% in borosilicate. These are different forms of glasses, and 100% as you see in fused silica. So fused silica essentially is the cleanest form of glass that is available, okay. And it has this silicon oxide in combination with some other metal oxides, okay, normally. So it has desirable properties like high mechanical strength, high electrical insulation, more optical transparency, and high chemical resistance, etc. And in case of photolithography and other kind of techniques, there are some commercially available glasses which you could actually photo pattern. One of them available commercially is known as photurin. It can be photo patterned directly onto the substrates, wherein it can be used either as channel material, where particularly you sandwich such a layer and photo pattern it and then cover it with another layer on the top and then thermally bond maybe. So there are embedded channels this way that you could make within a wafer. So glasses are mostly etched in buffer HF solutions, okay. So this slide really gives you some of the introductory processes to MEMS fabrication. So really this is all about formation of structures that could be used to form sensors and actuators, okay. That is all about MEMS. One shot MEMS is essentially how small structures can be fabricated and realized, so that they can be used as sensors or as actuation mechanisms, okay. And these sensors really do some processing, some transduction processing of one form of signal into another. So the signal can either be non-electrical or electrical. In non-electrical signals are particularly like piezo based or vibration based signals. And then we also know that most of the MEMS are used or made or realized by using conventional and new semiconductor manufacturing techniques, things like etching, deposition, lithography, oxidation, epitaxy, so on and so forth. You could also talk about some other specific to MEMS processes. Deep RI is one of them, where you actually build very high aspect ratio straight edged channels. You can talk about thick plating, particularly electrochemical plating, where a very thick metal layer is deposited and etched and characterized, etc. And really if you divide this whole machining, you can categorize them into bulk and surface micro machining. The bulk, as you know, is more related to the volume removal or the bulk removal of the material. This right here is an illustration. So this is the cross section of the silicon wafer, and you can use this particular red layer here as the masking or the masking layer, and you can actually etch away material underneath it using an etching solution homogeneously or isotropically. Or you could actually do a deep RI based etch, where you can have very straight aspect ratio or geometry of this particular channel. You have opened a etch window at the top here in order to accomplish this, and this is plasma driven process, and we are going to cover details of what plasma is in this particular topic or section in a few slides from now. This is another very interesting illustration. You are talking about depositing a P plus layer here. So this is P plus silicon in green, and you have opened another etch window, and then you etch the material in the bulk manner outside, so that you can realize this freestanding membrane like a flat beam, okay. So therefore these are really bulk micro machining process, where it is a subtractive method, it is removed from the volume of the material. The surface, on the other hand, is an additive process, okay. So bulk essentially is subtractive and surface is additive. So as you are seeing here in this particular process, you can see you are growing pillars, posts. This is a very fine illustration here. So this was a sacrificial material, as I am showing on the red shadowed region, and after depositing a layer of polysilicon on the top of it, you have removed this layer out because it is sacrificial. You can dip it in acetone or something, so you can formulate an embedded channel in the polysilicon layer and between this glass. But whatever it is, you are building it on the surface of a wafer. The wafer really is not subtractively etched out, it is additively built upon. So, that is what surface micro machining is all about. Okay. So, we talk about etching first. So, etching, as you see, is a process which is now illustrated here. So, you actually do introduce a blue layer, as you are seeing here, of a photoresist material, as you can see. So, this is the photoresist material and this is a positive photoresist. So, wherever there is an exposure to light, there is going to be a creation of a via or a capillary. Then you add a photomask, as you are seeing from this region here, made up of violet color. So, this is the photomask, okay, and then you are exposing this whole assembly to the UV by after putting the photomask directly over the photoresist. And so, as you actually hit it with light and then later on develop it, it creates two vias here on the resist. So, the remaining portion is still the resist, as you see in the blue, and this portion showed by the two red arrows here are really the resists which are removed, or the vias are created. So, therefore, whatever was there on the photo pattern, as you are seeing here as open areas, okay, these two areas which were open here have been translated in turn in terms of these vias on the photoresist. So, therefore, light fell on them and it got debonded, or and it could be removed or etched away. So, therefore, one more interesting factor is that it has exposed the underneath silicon surface here, which was the base wafer, to etching action. The other portion is actually a sacrificial cover over the silicon surface. Now, you could use some kind of a some kind of an acid, maybe HF, okay, or aqua regia or some of the acid to etch off this particular layer up to certain depth and then essentially remove the photoresist over it. So, okay, so this is the etching process. So, let us say in this case you are using 1 part of H2SO4, 8 parts of H2O2 and 100 parts of H2O, okay, by volume. And when you have etched away this particular layer, which was earlier gray, as you can see here, now this is the etched part. So, it is denoted by this light green, and so you are left with etched holes or vias, and then you can remove the photoresist away. So, that the original wafer can be turned with 2 etches on both ends. So, these are the relatively lower etch depths, as you can see here, okay, on both sides. So, this can be like kind of etched structures or features within the micron surface. So, this is how etching is done with a sacrificial layer of resist. So, let us talk about subtractive or bulk techniques first. So, the first kind of bulk technique is also the wet etching process. As the name refers, it is essentially a process of removing solid materials by dipping it in a chemical solution, which can violently react and create groups or move away groups. Thus, etching is performed in that manner. Okay. So, wet etching in microelectronics is mostly isotropic, independent of the crystalline orientation, etc., and is done with very simple methods which can homogeneously go on etching by using chemical reaction the bottom of the silicon surface. So, wet etching in microelectronics again are isotropic and independent of crystalline orientation. So, but then there is a potential pitfall to this problem, and that is basically under etching. And I would just like to illustrate here how this effect comes in. Let us suppose you have a sacrificial layer here, which is also like a masking or a protective layer, and you are using etch solution to pass through this particular etch window into this particular silicon, and it starts etching away. So, because it is a homogeneous etch process, the etching would be same in all directions, and therefore, this part which is away from the window is also started or also starts to get etched, and therefore, the overall etch shape is really much more in size than the etch window. So, this is really known as the under etching effect. Let us actually see how it happens. So, this is actually the mask window again, okay, and you have this layer of material removed from under the mask window, and this area, essentially this particular area, is also known as the under etch of this particular feature or structure. Now, one thing which is important to be noted here is that if suppose the etch solution is well stirred, as the etching continues, the shape will be more spherical in nature, as you can see here, because then the homogeneity of the etch is maintained, the solution is continuously recirculated across the edges of this particular illustration, as opposed to where it is not properly etched, then of course there will be a preferential etch direction which is more in the side than in the bottom. Okay. So, because essentially you can consider that more area is being exposed to the etch process in the bottom, due to which there is more amount of material dissolved from the bottom. Okay. And there is a concentration gradient which is created, as opposed to the sides probably where very less amount of material is withdrawn from, and that is because of the low etch rate in the linear direction. So, because of this reason, as you see overall, sometimes after a while this etch gets flatter, because this is diffusion limited process. The material which is getting dissolved and coming out is of course creating a concentration, and then this becomes slower and slower as it goes down, as compared to the other sides where less material has to be removed and the concentration is probably lower, and so therefore the etch can actually go ahead in properly. Okay. So, another important factor here is the type of materials, and then what it is selective to, and this has been illustrated earlier also, what you mean by etch selectivity. Selectivity is essentially the stopping process to the particular material. So, suppose in this case you have a silicon material and you have a SiO2 layer which is a masking layer or a sacrificial masking layer. So, you can say that this particular HF, HNO3, CH3COH, that means acetic acid, nitric acid and hydrofluoric acid in a certain ratio forms an etch stop over the SiO2, which means that it is selective to this, as opposed to silicon material where it is not really selective to. Okay. And so, therefore, it etches away silicon, but whenever it approaches a SiO2 the etch stops. Similarly, for a potassium hydroxide it etches away silicon with a selectivity towards SiO2. So, this table here really illustrates what are the materials over which the etchants are effective and what is the etch stop layer for those kind of materials. Well, these are some of the wet subtractive etching techniques, and this slide has been illustrated before. I would just like to kind of put it back again, that high etch selectivity is the necessary characteristics for silicon micromachining. This shows high etch selectivity where there is very low amount of substrate damage as the etch approaches an etch stop layer. So, really it is a very proper highly etch stopping layer of a certain chemical, but some chemicals do not pose this kind of a, some chemicals do not give this kind of a property, and it poses a problem by etching off the sacrificial layer, as you can see here. And so, therefore, the etch stop layer is really not one uniform, and that creates problems over the whole aspect ratios, feature sizes, etc. for this particular technique. So, one has to choose the etchant and the etch stop layer in a very good faith, so that there is hardly any substrate damage which would take place as the etch propagates. These are some of the common etchants for isotropic wet etching in silicon, as you can see here, and what it is selective to. I have just compiled the table that was illustrated before, and the second technique that I would like to point is called anisotropic wet etching. Essentially, this is the technique wherein a certain hydroxide based chemical process is used for etching of silicon. So, in this particular anisotropic etching process, the only difference that you have is that the etchant solution is a hydroxide based solution, and therefore, the process is really based on an electron transfer redox reaction which happens with silicon of the particular hydroxide etchant. So, as it is limited by a flow of electrons from the silicon structure, the problem that one would face in this case is that as the etching propagates or as the etching continues. So, as the etching continues, there are certain planes of silicon along which there may be a shortage of electron donation. Okay. Electrons are more firmly bound in those planes. Because of that, there are certain planes over which the etch rate is effectively the slowest, and as the process propagates, and ultimately the feature which is carved in the silicon is totally based on such directions where the etch rate is the slowest and the etching takes place the slowest. So, eventually the average feature which generates in a silicon because of this kind of situation is based on reflection of those planes where the electron transfer is the slowest. So, therefore, the H's happen eventually in the 111 direction. We will be clearing this point in a little bit later example, numerical example, when we try to find out such H planes regarding this process. So, in a nutshell, for a single crystalline material such as silicon, as you can see here, the etch rates of anisotropic wet etching really depends on the crystal orientation, and in an anisotropic wet etching process is essentially redox formulation where hydroxides react with silicon in the following steps. So, you have in the first step the silicon getting coupled with hydroxide which is generated from the etchant material. So, 2OH, and this gives SiOH2 with the 2 plus and 4 electrons here, and then this 4 electrons combined with the water which is present around, which dissolves the KOH or whatever hydroxide it is, and gives 4OH minus and liberates hydrogen gas H2 which bubbles out, and therefore, thereby the 4 OH, the 4 OHs which are generated here, and this is actually an OH here. So, 4 OH minus which is generated in the previous step here reacts with SiOH 2 plus, and this gives SiOH 2 minus and H2O. And if you just write the overall reactions, so these 3 reactions taking place kind of parallelly, if you react if you write the overall reaction by summing over the left and right sides, and thus the electrons and some of the species get cancelled, you are left with Si plus 2OH minus from the hydroxide plus the carrier H2O, the fluid, the water which is around, which would give SiOH2 plus 2, and this is actually in dissolved state. Okay, so, this dissolves very fast, it is an ion which dissolves fast in the solution and it liberates 2H2O. So, therefore, the silicon is really removed as SiOH2 plus 2 state inside the solution. It is a complex which is formulated inside the solution, and problem is that in the steps of reaction overall 4 electrons are transferred from each silicon atom into the conduction band. Okay. But if you look at the etching processes, really it is then a function of the presence or absence of the electrons. Now, manipulating the availability of electrons can make controllable etch stop possible, and that is happening because in its crystalline structure silicon atoms in 111 planes have stronger binding forces, and it makes the electrons to really lose their valence band configuration and get into that outer conduction band, and thus their availability, the readily or their ready availability is kind of very difficult. Okay. So, thus the etch rates at 111 planes are the slowest possible etch rates, and considering that to happen, really eventually the sides of the particular channel get shaped towards the 111 direction, because that is the slowest removal rate or the slowest etch rate. So, the basic silicon etchants, some of which provide the hydroxide groups, are alkali hydroxides like NaOH, KOH, CSOH, rubidium hydroxide, lithium hydroxide, etc. Then there are these ammonium hydroxide based etchants. One of the very popular etchers that are used are TMH based, it is called tetramethyl ammonium hydroxide, or simply ammonium hydroxide based etching. So, anything which can furnish hydroxyl ions easily, and then you have this other mixtures which can again give hydroxides. One of them is EDP, ethylene diamine pyrocatechol, or a mixture of ethylene diamine, pyrocatechol and water, which can give hydroxide ions readily. EDP of course is hazardous, and this causes cancer. So, they is not a very environmentally friendly process, and wherever there is EDP performed, and it is not very often used also because of this one factor, you have to have proper safety measures to use it. Other etchants could include hydrazine water complex or amine gallate etchants, etc., which can also just identically release electrons or release hydroxyl ions to initiate this redox process. Let us look into what really the anisotropic etchant shape would be, and what is the comparison with the isotropic process. As you can see here, some of the SEM images of anisotropic versus isotropic etches. This right here, as you see, is a spherical etch where etching takes place uniformly across all the directions. This is blown up by about 300 times using an electric field of about close to 0.8 kilovolts, and this right here is 33 microns, which means that this would be a couple of 100 microns, let us say about at least 600 microns or so along the etch window, and the depth again could be close to about 500 microns or about 400 microns or so. This right here again is done at about 20 kV, and essentially this is kind of an identically shaped corresponding anisotropic etchant used process. So, you can see that eventually the shape which formulates is dictated by the 100 plane, okay, or sorry, the 111 plane, which is in this case the least electron releasing plane or electron donator. So, therefore, it is an auto shaping technique of silicon, the anisotropic etching process. Let us now try to understand this process a little more mathematically, a little more closely. So, we have a case where let us say a microchannel is etched in a 100 wafer with a KOH solution, okay, the potassium hydroxide solution, and we have to determine the angle between the channel walls and the front surface, what really this angle would be, okay. So, we are talking about this particular angle theta that we need to detect here, and then we also are given that the top channel width and etch rates are respectively 100 microns and 1 micron per minute, and we need to find out what would be eventually the bottom channel width after about 20 minutes of etching process is over. And in the third question, we have to find out how long the etch process takes place till it stops as both the planes meet, essentially, because you know the 111 plane, as you know, is the slowest etching step that you have, and so eventually when you are going at a certain angle, it is almost always obvious to assume that they would kind of meet each other when there is an abundance of no other planes but the 111 plane, and so therefore the etch rate will kind of slow down, almost become negligibly small, 0 in that kind of a situation. So, we need to find out how much time it will take to arrive at that kind of a situation. So, let us solve this problem one by one. So, based on the crystal structure, the angle between the fast etching plane 100 and the slow etching plane 111 can be represented here, as you can see, by the angle alpha, okay. So, alpha is the angle which is between the 100 plane and the 111 plane, 111 plane of course being this one, this is the 111 plane, the triangle is the 111 plane, and this is the 100 plane, okay. So, the angle is really the angle between these two planes, as is accurately represented here by this angle alpha, all right. Alpha is this angle between these two vertices, or whatever you can call. Let us try to determine this. So, based on the crystal structure, the angle between the fast etching plane 100 and the slow etching plane 111 is the angle ABC, okay. This is B, this is A, this is C, let us call it alpha. So, how do you find it? So, let us say in triangle DAE, this is D and this is E vortex. So, let us say we have to see what is essentially the characteristic feature of this AB, which is also a kind of median of the triangle DAE. So, in triangle DAE, with the angle DAE really equal to 90 degrees. If you look at the angle here, this angle DAE is 90 degrees. Okay, DA is this one. Okay, so it's like basically the two coordinates x and y perpendicular to or orthogonal to each other. So, so basically the height in this case AB. So, let us just draw this triangle out here. Okay, so you have a triangle, both, mind you, these both are 1. So, this is root 2 and this is 90 degrees. And essentially you are doing this in a manner that this is, so this is basically a kind of isosceles triangle with this angle equal to this angle equal to 45. So, this would the median would be actually a perpendicular line which is actually equal to. So, you look at this particular triangle now, which this is root 2 by 2, okay, this is 1. So, naturally the other part here would be root 2 by 2. Okay. So, really AB, this is B, AB is root 2 by 2. So, the height AB here is root 2 by 2, all right. Similarly, in triangle ABC, this followed by this, which is the 0 1 0 direction basically. So, you have another case here which is very interesting. So, let us say you take this triangle off here and draw it. You have one side which is 2 root 2, 2 by root 2, root 2 by 2, another side which is 1, okay. And essentially the angle between this side and this side is alpha, right, that is what this is about. So, I am actually taking this inclined triangle, and trying to flatten it up like this. So, that is what it is going to be. So, you have root 2, you have 1, you have you have root 2 by 2, you have an angle alpha and you have 1 here. So, naturally if this is 90 degrees, because this is going to be 90 degrees in any case, the side BC is essentially root 3 by 2. Okay. So, the side is root 3 by 2, and I am not really worried about that. What I am worried about is what this alpha is. So, alpha essentially can be given by, so tan alpha is in this case 1 by root 2 by 2, or it is root 2, or alpha is actually equal to tan inverse of root 2, and root 2 is 1.414. So, the tan inverse of that is essentially equal to 54.74 degrees. It is more than 45 degrees, tan 45 is 1. Okay. So, therefore, the alpha value, the angle here is 54.74 degrees. Now, we know that after 20 minutes, so the first part is answered. So, first part is basically what is the angle of the plane finally formulating. So, the angle of the plane finally formulating in this anisotropic etching process with the direction of the face of the wafer is really 54.74 degrees. This alpha here, this is the phase direction of the wafer, this is the angle of the plane. So, this is also the 111 direction, alpha is 54.74 degrees. And let us find out what happens after 20 minutes. So, after 20 minutes of etching, with an etch rate of 1 micrometer per minute, the channel depth D is really nothing but, it is like 20 times of 1 micrometer per minute, which is actually the etch rate which is given, the vertical etch rate which is given. So, it is about 20 microns, all right. So, if it is about 20 microns, then the bottom channel, so basically you want to find out what is the bottom channel width. So, let us draw this figure again. So, you have a case here where this angle right here and here is 54.74 degrees, and this distance which has been etched off or etched away is 20 microns. So, therefore, the bottom width here WB, and this is actually the top width, okay, WT, which is equal to the bottom width WT minus 2 times of d by tan alpha. Okay. That is what exactly the WB is, the bottom width is. So, WT minus 2 by d by tan alpha, and essentially the top width, as you know, WT is nothing but it is equal to about close to 100 microns, as has been suggested by the question itself, that the top window, the top channel width is about 100 microns. Now, so if that is so, we have the bottom width here is 2 times of d by tan alpha. D is the h depth is about close to 20 micrometers, and tan alpha is essentially again root 1 by root 2, as we know. So, it is essentially nothing but 1 by tan alpha is root 2, I am sorry. So, tan alpha is about root 2. So, essentially this whole thing boils down to, let me just rub this and rewrite it again, root 2. So, this whole thing boils down to 100 minus root 2 times of 20 microns, which is actually equal to 71.7 micrometers. That is exactly what WB, or the bottom width, is in this particular case. Okay. So, if the etching process stops, so the etching process would stop again as and when the bottom width WB is 0, as you can see here. All right. So, here what happened is this was the top width WT, this was the bottom width. So, WT minus 2 times of d by tan alpha. So, this is d, this essentially is d by tan alpha. So, you are actually subtracting both ends 2 d by tan alpha in the process, okay, from WT. So, here if WB is 0, then the maximum h depth that would be needed for the WB to be equal to 0 is essentially equal to d max is WT by 2 tan alpha. Okay. And in this particular case, as you see here, WT by 2 tan alpha would be actually equal to about 70.7 micrometers. And time t again would be equal to d max by 1 micrometer per minute, which is the h rate. So, it is about 70.71 minutes. So, that is what essentially the time until the h stop is achieved would be. So, it goes all the way to about 70.71 minutes, which is also corresponding to 70.71 microns, where the bottom width WB becomes equal to 0. So, now I hope you are kind of aware of this whole etching business and the way that anisotropic etches can be accomplished. So, I would now like to move on to the dry etching processes, which is by using plasma techniques. Okay. And essentially dry etching, as you know, is again a process where material is selectively removed by an agent which may be in the liquid or in the gaseous state. Okay. So, here the dry etching can be categorized as physical dry etching, okay, or chemical dry etching primarily. Physical dry etching, as you know, it utilizes beams of high energy ions, electrons or photons whenever lasers are involved, electrons whenever e-beam machining is involved. So, this is essentially to bombard the material surface, okay, and the kinetic energy of the ions knocks out the atom from the substrate surface in that particular case. So, high energy beams really then tend to kind of evaporate metal atoms from the knocked out materials, and the basic mechanism is ablation. The basic mechanism of material removal is material ablation. So, there are some limitations in this high energy physical etching, physical dry etching process. Now, the major limitations are the slow etch rates, because you have to individually ensure that all the atoms and all these molecules are knocked off and vaporized completely from their solid bounds to a state where their mean distance goes at least 10 times more than the the distance of solid state or liquid state. Okay. So, low selectivity is also one of the major problems with this particular process, because the ions attack essentially all the material surface which is available. It does not distinguish between material which is covered versus material which is exposed. Okay. It is an ionic kind of beam which you are falling on the material. So, wherever it would hit the material, it would immediately start attacking the metal or material non-selectively. So, there is nothing called etch stop until you reduce the beam power to 0. Essentially the etch stop is when the beam power falls down to 0, it is only controlled by beam power. So, there are other problems or issues. One of the major limitations is what we call trench effects, which are caused by reflected ions. So, you have ions spotting into a, let us say you have, this is the spot where this high energy beam is being focused of this particular ion, okay, and you have sputters of material all around, and this causes the trench effects, which means that some of the ions heating away from this sputter actually starts hitting onto the edges, and edges develop these trenches like features, which is very, very common to this kind of physical dry etching. The other kind of technique is chemical dry etching, where you have actually a gas which is an etchant gas which chemically removes away the material. Okay. So, you have essentially a chemical dry etching reaction between the substrate surface and the gas that you are supplying. So, gaseous products are conditions for chemical dry etching, because deposition of reaction products will stop the etching process. Okay. And basically chemical dry etching is also completely isotropic in nature. The technique is similar to other wet etching forms, exhibits relatively high selectivity, because again because it is a chemical removal process, the chemistry is actually the determining factor. So, if you make a different chemistry which is unsuitable to etching, it can act as a etch stop layer very accurately. Well, that is what dry etching is about. Let us actually see how this dry etching process can happen. Like for example, in case of silicon atoms, if you hit fluorine inside a silicon matrix, it starts immediately forming silicon fluoride. This is SiF2 which has been formulated, still it is unbound. There is another fluorine addition which happens, and then finally another, and so this SiF4 essentially is a gas phase material. Okay. So, it is a gas phase material which would kind of leave the surface. Also, you have to see that you have satisfied all the bonds associated with silicon. So, the unsatisfied silicon is kind of left bound in the lattice structure, and the silicon here, which was initially there because of unsatisfied bonds, now have been satisfied by fluorine, and it leaves away as an independent entity or a gas. So, therefore, wherever silicon goes off as SiF4, you have trenches or vias which are created, and it is essentially a chemical dry etching process. As a reaction is happening, there is a gas phase which is sending in, and there is a dissolved gas phase of silicon which is coming out essentially of the process. So, some of the recipes of dry etching gases are, like for example, for material silicon with a selectivity to SiO2, you have these different boron trichloride chlorine, boron trichloride carbon tetrafluoride, boron trichloride methyl trifluoromethane, you have chlorine and CF4, so on and so forth, and so therefore, if you have to remove material SiO2, it is selective to Si or aluminum layers. These are some of the gases which are used, and so on and so forth. So, this table basically is a kind of complete recipe of dry etchant gases available for thin films, functional materials which can either use chemical or physical processes to remove off the material. Okay. So, another very interesting kind of dry etching process is a physical chemical. It is a combination of a physical as well as a chemical dry etching. Okay. So, these really are called reactive ion etchers or reactive ion etching process, and it depends on the pressure zone in which a plasma has to be created over a surface. So, essentially there is a chemical gas phase reaction which is responsible for etching, but it is done within a plasma atmosphere where there are ions and electrons of this gas, and there is a certain drive pressure or an ionic momentum which is imparted to these species. It can drive into a substrate and start removing material from the substrate. So, therefore, based on this RIE processes, there are different kind of sub processes like anodic plasma etching, magnetically enhanced reactive ion etching, MERI, triode reactive ion etching TRI, and transmission coupled plasma etching TCPE. So, there are different kind of reactive ion etching processes that one may think of in the physical chemical etching area. Some of the other important processes which are used are chemical vapor deposition reactors, where these chemical etching can be carried out. So, typically you have a substrate as you can see here, and you have a set of heaters which would be able to heat the substrate to a certain temperature. You have an inflowing reactant and a gas inlet and a byproduct gas outlet. The heaters are actually on both sides so that you can uniformly heat the substrate, and then definitely this is actually what a horizontal reactor would look like typically, and then you flow in, flow out the gases which would cause the reaction on this substrate, and there would be a gas state which is dissolved, and the gas finally goes out from this outlet end. Similarly, in case of a vertical composition of the reactor, what happens is that you have a gas inlet which is thrown into this area where there is a reflecting plate, and the ions are reflected off and removes the material, and this is highly heated zone with this resistance set of heaters, and then therefore whatever is removed here is, or whatever is produced here is again removed by the exhaust system continuously. So, there is a flow between the reactant and the gas inlet. So, there is going to be sufficient amount of laminarity or turbulence which is introduced by the various flow velocities that are achieved within this particular kind of vertical reactor. So, you have a horizontal reactor and you have a vertical type of reactor for chemical vapor deposition processes. So, this slide here illustrates how you can etch cantilevers and diaphragms using wet etching techniques, and I have, I think, illustrated this before, but I would just like to go through it once more. So, you have let us say a P double plus etch top on the top of a silicon, and you are actually opening a small window here on a sacrificial material masking layer which is made in this black here, and through this window you etch using anisotropic wet etching, so that you formulate on both sides 54 degrees angle of the walls. So, you typically put a hydroxide etch, and then you are left with this P plus membrane here which is only a few nanometers, and it is like a vertical membrane, it is a simply supported beam or a membrane which can be used for various purposes. If you could have used, instead of anisotropic, isotropic wet etching with slight amount of stirring, then the etch would have been spherical in nature, and therefore you can actually get again the same formulation of a thin membrane on the top of this this semi-spherical kind of structure which is used or generated by isotropic etch. You would like to, so this is how a diaphragm could be manufactured. If you on the other hand want to manufacture a cantilever, the best way to do that is to put a sacrificial layer as you are seeing here on the top of silicon, and then you cover it with a polysilicon or an active layer by some deposition mechanism, thereby removing this material back, so that you are left with a freestanding membranous structure over silicon. You could use another masking alternately to remove material from this end, so you have a perfectly kind of separated cantilever structure for different diagnostic studies. Now, I would like to come to the next process, which is photolithography. Okay, so therefore, we are kind of towards the end of this lecture. We will try to introduce some more processes like photolithography and other deposition techniques like sputtering or ion implantation in the next lecture. Okay, thank you.